Okay, so welcome back to the afternoon session. So we have the second part of the mini course by Sang-hyun from KIS and about structure and rigidity of diffeomorphism groups.
Okay, thank you very much for coming back again. So before we begin, I'd like to mention that most of the material that I'd like to talk about, at least like more than 2/3 of the material that I'm talking about, will be in this book, Reference Structure and Regularity of Group Actions of Manifolds. It's 2021. It's written by me and my collaborator, Thomas Caberda. It's free to download on either Springer website and also on the archive. So if you're interested in the details, you can check. And also, I'd like to mention about some of the questions that were raised yesterday. So I didn't really have time or to talk about them in detail. So first of all, there was a question by Near about continuous homology. So the conjecture or question is that if you consider homology of diffeomorphism group, so in other words, consider, so homology of a group is defined as the homology of the classifying space of the group. So you can consider TIFR of, say, let's consider Mn of, say, compactly supported identity component. And the question is, are they the same as classifying space homology when considered as topological groups? So I put delta, means that you completely forget the topology of the group. You just consider it as a discrete group and just construct classifying space and compute the ith homology. And this is topological groups, classifying space and ith homology. And this is basically this is known for the case when we know diff group is simple. So I call 0, this is true for all R. Oh, sorry, right. For all R equals 0, so homeomorphism group. For all I, this is true. This is Metter's theorem, 74. And R equals 1. This is amazingly true for all I. This is true by Metter and Thurston. True by Zboy, 1980s. Except for the case, right? So, and also R, so conjecturally, for all R and I between 0 and up to dimension of M. And also, we are interested in I equals 1 case, right? So I equals 1, actually I equals 0, 1, 2, true, possibly except for a problematic case, R equals n plus 1. Because, well, so how do you prove such a thing? You consider this homotopic vibration sequence. So there is a trivial map from this group, discrete group into topological group, which is continuous map, and you put it in some Viber sequence, and you just compute the homology group. And the simplicity is very useful tool to compute the 0, 1 second homology group. So for this case, everything is fine as long as we know the simplicity of the diffeomorphism group. But if we don't know. So not much is known, and conjecturally, this is true for all regularity up to dimension M. And I larger than dimension M, there are counterexamples, I think, even for circles. So this is something that I'd like to mention. And I guess our near question is specifically about I equals 1. So this almost known except for the problematic case.
Regularity R equals 0, 1.
Oh no, this is dimension. So regularity is R, and I is the homology dimension.
Is that I equal to just 0, 1, 2, or does it go on?
No, it does. So conjecturally, it goes on. For all regularity and for all degree, they are believed to be isomorphic, but people don't have much idea about it. But computing these groups are very hard. So this is one of the questions raised yesterday. So another question was right. So some easier one, right? So also this is nearest question. So F2 cross Z star Z is residually diffeomorphism group. Diff infinity I. So actually, yes. So a lemma actually which appears in that book, possibly known to experts before, that if G0 and G1 is C infinity diffeomorphism group of compact interval, then free product is residually if infinity plus I. So just to rephrase, this means that for all non-trivial element in the free product, there exists PG under which G survives. So this is an exercise in ping pong argument. So you write G as a normal form, like some elements from G0, G1, G0, and G1, and make sure the action of G pushes some point to the right and to the right, for each syllable. Sometimes you might have to reverse the direction, but in that case, you take a opposite representation of the group. So you can revert the direction so that element, so if this is written as a G1, G2, G1 prime, G2 prime, then G1 is doing this thing, G2 is this thing, G1 prime is this, G2 prime is this thing under phi G. So in particular, yeah, that group, or anything that looks like that group is residually diff infinity plus I. Yeah, so last night I tried to do my homework. Are there any questions? So another question, well, actually, yeah, right, was so the variety of these critical regularity groups. So there exist many GR with critical regularity R. And the answer is yes, as I said. So one way of expressing it is as follows. So consider alpha as a concave homeomorphism of 0 infinity. Concave homeomorphism. Then such a map can be used to measure the continuity of a function. In other words, what is it called? Modulus of continuity. So in other words, you collect all the k comma alpha of a manifold that is in the k of m, such that the alpha, kth derivative is alpha continuous. What is this? So supremum, everything is compact, so x naught y, kth derivative of x minus kth derivative of y, take the operator norm difference, and distance x, y, and you feed it to alpha is finite. So this is the definition of alpha Hölder continuous for a function alpha. And nice thing about assuming the concavity is that this becomes a group. Without the concavity, this is not true, but the advantage of assuming the concavity. And concavity is actually enough. Every modulus of continuity is bounded above and below by a constant multiple of some concave modulus of continuity. So concave is enough, and it gives us a group. And our theorem is basically for all K and alpha, we build. So up to some error, we build a group G K alpha inside diff K alpha, such that the regularity cannot be enhanced by considering another embedding. So in particular, you can consider this kind of modulus continuity. So this is exponential of, say, minus tau log 1 over x. So this is nothing more than x to the tau. That's x to the tau. And then you add some terms of smaller order. Say tau prime of, say, square root of 1 over log x. And tau 2 prime of, say, cube root of 1 over log x, and so forth. Right. Then these are very slight perturbation of tau Helder continuous. And if you only care about critical regularity, measuring supremum of the real number that R that it embeds into TIFR, they all have the same critical regularity tau. In other words, critical regularity of this group, G of K comma alpha tau prime is K plus tau. Right. So let's call this as alpha tau prime tau 2. Therefore, by varying tau prime, you obtain uncountably many critical regularity R, K plus tau group. That's once you have the right theorem, there's an easy way of producing many pairwise non-isomorphic group having the same real number regularity. Yeah.
Some of them, some parameter values are actually finitely.
Very good question. I have no idea. I mean, we try to solve it, really try to solve it, but our method doesn't work. Our method is just giving you functions rather than some algebraic construction. But I think that's a very interesting question. Another thing that we do not know is that does there exist, it's not known, I guess, that does there exist a group finitely generated which admits some embedding into diff K for OK, but not C infinity. So for each K, you can build an embedding, or even like some non-trivial action, but every action on C infinity should be trivial. So that our method does not give that either. And another question that was raised yesterday was by Mahan was that what's special about the regularity n+1? So I guess I owe some explanation because it's quite interesting phenomenon. So let's just consider, say, diff2 of R compactly supported. So we do not know whether this is simple or not. But Mether's approach, so the known approach, is trying to prove this, the simplicity of this group is decompose this thing into if 2 comma alpha of C, where alpha is concave homeomorphism. So as I said, this is equality. Any C2 diffeomorphism group will have some modulus of continuity, and that some modulus of continuity can be chosen as concave homeomorphism as that form. And then the strategies show that this is perfect. Because in this case, we have certain concave modulus of continuity, so you can apply some functional analytic tools such as Arzelà-Ascoli theorem to show convergence of infinite sequence and find some commutator representation. So yeah, Arzelà-Ascoli theorem is basically the only existence tool that one can use in this group. So we want to show that this is perfect for each alpha. And this is true when alpha is Hölder continuous, but what is not known is, I'll just abbreviate, question mark is, say alpha x is very large concave modulus continuity, such as say 1 over log 1 over x. So this is something that converges to 0, but very, very slowly as x goes to 0. So so in this case, we do not know whether the 2 comma alpha CR is perfect. And let me probably in 5 more minutes, I'll just follow Matter's proof to trying to show that this is perfect and show you where it fails. So the approach is as follows. So consider any F in the group. Let's call this as G. You may assume that G is very near from the identity because, because any identity neighborhood will generate the group. So you may assume that F is very near from the identity. And the goal is to show that F becomes trivial in the H1. That's the whole goal. So the idea is the following. So we want to build some map, say TF, from identity neighborhood to the identity neighborhood inside the group where the norm is this 2 comma alpha norm. Is supremum of that thing. So 2 comma alpha norm. C 2 comma alpha norm, where I didn't erase it yet. Supremum of the difference of kth derivative divided by alpha Hölder continuous. Hölder value. So build TF, which is supposed to be CK compact continuous. But nice thing about this B epsilon norm, the epsilon neighborhood with respect to this norm, is that this is compact. So C2 compact by Arzelà-Ascoli. Because you are controlling the continuity by modulus continuity, so equicontinuous, so it is a pre-compact, so your closure is compact. So build so you can apply fixed point theorem. So build such a map such that TF of G, whatever you put, this is same as FG. So this is our goal for G. So once this is achieved, suppose we have built such a thing, then we are done. Because we have some fixed point. Therefore, G naught is same as TF G naught, which is by requirement FG naught. So we have just shown that F is trivial. Sure, therefore, F is trivial in H1. So the game is find some clever definition of a map from a ball to ball, such that H1 class is preserved. In other words, starting from FG, you multiply some of the commutators, and like conjugation is allowed. And eventually you want to reduce the norm, that's all. How do we find such commutators? So first trial is you may want to try just simply TF of G is FG. But this will fail by triangle inequality, because if you take the norm, then this is roughly, so this is 2 alpha norm, so there might be some error term, but this is, you can show that this is less than 3 epsilon, but not less than epsilon. So you cannot define TFG as U. You have to do some manipulation so that H1 class is not changing, but still the norm decreases. So the next trial is variation of U by making an act on a larger interval. And that almost works. In other words, define U1 X as the, say, some large number, FG, some divided by large number. So U1 will act some large interval. If the original I is the interval -1 and 1. Then we almost win because U1 norm, if you compute alpha norm, then this is, what is it? You're computing supremum of, you take a second derivative of this thing. So let's see, I'll just, supremum of U2 prime x over n, 1 over n, minus U2 prime y over n, divided by so you just compute multiplication of x over n minus logarithm of y over n. So this is 2 alpha norm. I just computed the 2 alpha norm, where alpha is one negative, is inverse of logarithm. Okay. And you have this -1 over n factor. But then you didn't do any better because you can just substitute x prime for x over n, y prime over y over n. So this is just precisely the same as 1 of U norm, alpha norm. So we have increased the norm by 1 over n. But the problem is we have changed the domain. So we have to put it back in -1 to 1. So U2 is some circle diffeomorphism by averaging U1. So I cannot explain what I mean by averaging in 2 or 3 minutes, but it's basically you have some diffeomorphism on this big interval, and you just make it somehow just duplicate it again and again and again, so it acts on the circle. So that and then I'll talk about how to make it to real line action. So then, and the requirement is U2 is at most Cn of U1. So this averaging process certainly increases the norm, but only linear factor of the interval length. And then you make U3 acting on original interval again by spreading U2. Okay, so this is, I can only very vaguely explain this. Something is acting on the circle, then so U2 is acting on the circle, and then you find a certain U3 acting on interval of the same length or twice the length, such that it came from U2. It is just you make sure that some part, this is composed with the multiplication of 2 diffeomorphism acting on the interval. No, right, that's right. First of all, so you start just need to make sure that at least like one thing is fixed. You're right, and then you spread it, and then you spread it. And the point of spreading is that such that it is almost the same. U3 norm is almost the same, and the class didn't change. And U1 is trivially homologous to U because it is just linear conjugation. Then TU is defined as this TF of G. Then finally, this TF of G will be constant times n and 1 over n. So it is some constant times of u. So this is, say, 3 epsilon, 3c squared 3 epsilon. So this doesn't work because this constant may be larger than 1/3. But in all other cases, it turns out that this is less than, you can make it less than epsilon. In other words, in all other cases, you have a higher power, for instance, 1 over n squared, if you take third derivative. Therefore, 1 over n squared persists. Therefore, there's 1 over n in the end. So you can make it smaller. Even Hölder continuity, if alpha x were, say, x to the tau, then you would see 1 over 1 plus tau instead of 1 over n. Therefore, there will be 1 over n. So I should use different color because this is different situation. If alpha x were Hölder continuity, then you would see 1 over n plus 1 plus tau. And this averaging spreading process, the order of the increasing is the same, still constant times linear. Therefore, you will be able to make it the final thing less than epsilon. But only in this 2, very slow concave modulus case, it doesn't work. So that's, so I guess, well, I believe one would need the different definition, but the approach is generally fine. So you just need some other clever way of defining the operator such that H1 is still preserved, but reducing the 2 alpha norm. Okay. Any other questions? So that's about the questions raised yesterday. In dimension 1, yes. Right, it's fine, it's fine. So actually in diff1, it's you consider something different. You start from some interval and you actually contract it. But still in the case it works, yeah. No, so still it doesn't. Well, n greater 2, then it doesn't work for the regularity n plus 1. Yeah, it's completely fine. Yeah, sure. Because like, for example, if I'll use different color, if say you're considering say 3 tau. So you always need some modulus continuity, but 3 tau, then you will see n squared here.
This is the limit from Bob to critical.
Yeah, that's right. Yeah. And lower regularity, so this part and this part are exactly the same. You only need to change this part.
It's 1 by n FG and x.
Right. And then you do the same thing. Yeah. Okay. So this is a very short summary of matters proof up to very beautiful definition of this averaging operator. So I think that's very beautiful, but you might want to take a look at later. So today I'd like to talk a bit more about critical regularity of one-dimensional actions. So let me begin by explaining why one manifolds. Before we begin, maybe I'll just mention another thing that is related to yesterday. So we talked about Takens-Filipkevich theorem about isomorphism rigidity of diffeomorphism groups, that if two diffeomorphism groups are isomorphic, then regularities are the same and manifolds are diffeomorphic. So actually that can be generalized a little bit. So you can consider, say, CK diffeomorphism compactly supported isotopic to the identity. So identity component of compactly supported diffeomorphisms. So take anything between diff K and say L C0N of H N, and if they are isomorphic, then they are induced by conjugation. Conjugating. So listening to Neil's talk, so this is something like conjugation rigidity. If you just consider the case that K equals L and M equals N, that means that if you have two isomorphic groups in between, then they are conjugate. It's like something much stronger than finite index rigidity. But these are continuous groups, so in some sense they have a lot more things to use. And today I'd like to talk about one-manifolds. So why one-manifolds? So one of the motivation that especially foliation theorists look at this one-manifold diffeomorphism group is there's a canonical way of making foliation from one-manifold diffeomorphism groups. In other words, so you consider, say, homomorphism from, say, pi1 of some base manifold or orbifold into, say, CR diffeomorphism group of circle. Then there is a one-to-one correspondence up to conjugation. Foliated S1 bundle. Foliated S1 bundle over B. In other words, you construct so-called, yesterday it was called a Borel construction. So consider universal cover cross S1 quotient by for all fundamental group element. You identify XT with row deck transformation action and representation action. So this is typical construction, and this has S1 bundle structure over B. And up to bundle isomorphism, there is a one-to-one correspondence between conjugacy class. So actually, for students, I think this is interesting to note that if you replace this automorphism group as a automorphism group finite set, in other words, as symmetric group of N, and say instead of S1, you consider finite set N, then this is precisely what Doron was talking about. So this is a classification of covers, index N covers of the base manifold B. So, for instance, Ziboy and Cantwell-Conlon about the same time. (1989) or so. Yes. A foliated. So this is not a general S1 bundle. This is because this is a. I'm only talking about the S1 bundle constructed in this way. Yeah. So, and especially this is interesting as a foliation even when S1 is I, although topologically you can only see I cross manifold.
Basically recording the momentum.
Yeah. So monodromy is supposed to be a homomorphism instead of germ homomorphism. So they proved this some result purely about one-dimensional diffeomorphism group. That is, there is some group L, some finitely general group. Actually, this is very concrete. It's Z to Z. So this is, in other words, there's some lamp lighter that tau and infinitely represented group. So this is the group. Then for all k, there is a representation of L into diff k plus I, such that rho k is not conjugate, C0 conjugate. That means you cannot find homeomorphism conjugating rho k into diff k plus 1. So this is just purely one-dimensional diffeomorphism result. It's proved by Zboy and Hantel-Connon. But the reason why they considered is that using this, they were able to construct that there exists CK foliation on I bundle that is not conjugate. To CK plus 1 foliation structure. So this is I bundle, so this is just thickened surface, but you can decompose this space as union of surfaces, which could be just even like hyperbolic plane. But you cannot topologically conjugate it. Even if you apply suitable homeomorphism, you cannot make it to that the transition map is CK plus 1. The transition map is only achieved to be CK. So, and then they just precisely use this foliated I bundle structure of that blackboard and use this numbers. Right, single is genus G surface. So, right, so that is L, but what you do is genus say G surface fundamental group surject onto free group surject onto L, and you use diffeomorphism. And using this composition, you construct I bundle over sigma G. Okay, so this is one of the results related to foliation theory and why they cared about this one-dimensional diffeomorphism groups. But this kind of phenomenon is called topological smoothing. And what we are aiming to prove is something stronger. The topological non-smoothability. Non-smoothability. And we are actually trying to prove that algebraic non-smoothability. So for such a result, they prove that the group is fixed. The group is fixed, and even it will be injective in their specific example. But they are trying to prove that whatever conjugation you consider, you cannot embed into diffeomorphism group. And algebraic non-smoothability is more flexible. So you want to consider, or more rigid in other sense. So we want to prove that whatever homomorphism you consider, it cannot be injective. So G is algebraically CK smoothable if there is a rho K sending G into if K of interval or circle. So if something is algebraically non-smoothable, then trivially it is not topologically smoothable. But in the case of like this lamplighter group, the group itself might allow some C infinity embedding, but specific representation might not be able to be conjugated into any smoother representations.
Can you repeat the difference between topological smoothability?
Right, so a group is algebraically CK smoothable if and only if there exists some representation into diff K rho I. So doesn't care where G came from. It only remembers algebraic structure. But for topological smoothability, you care about the representation. So rho into diff, say, whatever, say some homeo, should be homeo. So embedding is given, is CK topologically smoothable if there is a homeomorphism such that H rho G H inverse is inside if K plus I. The topological smoothable means you already have an embedding and you want to upgrade the embedding by basically renaming the points of I or conjugating by I. So, right, topological smoothability trivially implies algebraic smoothability, or algebraic non-smoothability implies topological non-smoothability. Yeah. Right, so for countable group, yeah, they're the same thing. So this hypothesis is same as in the case of countable group. It is same as assuming that G is orderable. It's some specific order. And it is asking whether you can upgrade the order to CK diffeomorphisms. Right, so that's a great question. I'll just write in 2 minutes, I'll talk something about it, but full characterization seems quite hard. Okay, so, right, so actually that is the whole point of this study. So how much algebraic properties can you deduce necessary or sufficient for each regularity? So one precursor, say, is due to Thurston versus group theory. So there's a theorem called Thurston stability theorem about the foliation. 74. So the statement is, if you have a certain compact, connected, co-dimension, one, C1 foliation. So M is a manifold, and F is a foliation structure. In other words, decomposition of the M into co-dimension one manifolds, such that the transition maps of the chart are C1. And also you assume that there is some compact leaf such that it is finite H1. In other words, H1 is finite. 0. So abelianization is finite. Fundamental group of that abelianization of fundamental group is finite. Then there is this just amazingly it becomes very simple. Either MF is simply L bundle, L cross I, trivial I bundle, or L bundle over S1. This is an extremely powerful theorem, knowing only one of the shape homology of leaf. And if you look at the proof, the heart of the proof is this very simple looking lemma. Thurston, so some people call it a Thurston stability lemma. That for all non-trivial finitely generated group inside diff1, H never surject onto Z. So in other words, this C1 diffeomorphism group is locally indicable, if you already know what that means. It's just whatever non-trivial finitely generated group you consider, it can never surject onto Z. It's surject onto Z, surject onto Z. Right. So for example, if, right, you can consider like Thompson's group or something. Any group that can be smoothly embedded into C1 diffeomorphism group, diffeomorphism group interval, then it must surject onto Z. So this gives you one necessary condition.
You are constructing for base X with transitions to this
Oh, you mean the proof of Thurston stability lemma or Thurston stability lemma proof? Right. Yeah. So the proof is actually yes, something like that. Something like that. Right. Right. So what is it? The easy case is that so first trial is you just map G2 log G prime of 0. This is certainly homomorphism, but it may be trivial. So you just consider the case is trivial. That means, or even any larger numbers, that means, say, 0, everything is tangent to the identity. All the group elements are tangent to the identity. Right. Then you consider certain sequence, any sequence, right, going to 0, right? And then you consider, so in Thurston's word, in his paper, these diffeomorphisms act more and more like translation. And translation has homomorphism. The translation part is homomorphism. So he's exploiting that. So he considers, I guess, delta G of X, which is Gx minus X. But everything is finitely generated, so you can normalize it. Max of SIX minus X. And just consider this value and prove that this becomes homomorphism. And it is by definition non-trivial. And the reason why this is becoming homomorphism is that just what he said, just it acts more and more like translation. Therefore, delta G compose H is almost like delta G plus delta H as n goes to infinity. Yeah. Yeah. But this is a homomorphism. Yeah. 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 So this is a interpretation by Christian Bonatti. In his paper, it's basically the very similar idea, but in some other phrasing, that like you consider some kind of a quasi-homomorphism in larger and larger balls in the Cayley graph, and eventually it becomes homomorphism by choosing a subsequence of subsequence. So actually, you need something more than this. Nothing more than this. This is a special case. You will have to consider actually not just the diffeomorphism group, but germs of homomorphism, because that is what holonomy map is doing. So if you have a holonomy map, then you consider all the germs of diffeomorphisms near 0, and then just right. Something like pion of M. But more precisely, you will have to consider C1 germs of diffeomorphism groups and homomorphism from pion of L into that thing. And then this lemma will give you that pion L cannot be trivial. By assumption, this is trivial. So right. So you cannot have any other non-trivial holonomy, right? Yeah. But as I said, this is like heart of the proof. Not exactly the same lemma that you can directly use. Okay, so right, so this is one algebraic necessary condition. So if something is C1 smoothable, algebraically C1 smoothable, then it must surject onto Z. And of course, like people for some period, people try to prove the converse. Like if it is locally indicable, is it an orderable? Is it necessarily C1 smoothable? But it is not. Local indicability is characterized in terms of orders, so-called Conradian orders, but it doesn't give you C1 smoothability. So there are counterexamples by Andre Navas that some group can be locally indicable, but not C1 smoothable, algebraically C1 smoothable. So anyway, so Thurston then gave probably the first example of some algebraically C0 smoothable, but not C1 smoothable group. So that is, you can construct something like this to consider this group, say, P is cipher fiber space fundamental group. So P is actually not doing anything, so you can just erase it. So it's surject onto the hyperbolic 237 orbifold group. 237 order hyperbolic orbifold group, surject onto Z. And this is Fuchsian. So this is circle homeomorphism group. Actually, it's even analytic. And therefore, it lifts to the universal cover, which can be realized as the periodic real line, Z periodic real line homeomorphism group, and Z is the translation. And therefore, this group is trivially orderable because, so trivially C0 embed. There's a C0 action from this cipher fiber 3 space group onto the real line. It's trivial, but it is easy exercise, like to see that this is finite. It doesn't need anything. You just declare that it's abelian, then you see that this group is finite. Is it trivial? Yeah, it's trivial actually, right? Therefore, T can never embed into diff1. So this is what he mentioned in the same paper. So there are groups which admit C0 action, but not C2 action. And so you can, yes. Homeo-ZR. So the collection of real line homeomorphisms, orientation preserving, commuting with length 1 translations. So it's basically collection of lifts to the circle homeomorphism groups. All right, right. Because if it were inside diff1, and because it's finite generated, so it must surject onto Z. But abelianization is trivial, so there is no way that it surject onto infinite abelian groups. So critical regularity of this group is 1. So why is it? Well, actually, it's a very important but general fact due to the wrong Epstein. Yeah. Oh, is this just universal cover or just more geometrically all the lifts into real line action? Right, right, sure, yeah. You mean this arrow or? Yes. This arrow, right.
Circle action on SL2R.
Yep.
Maybe something like you're identifying the circle on the boundary as the unit diamond square at it.
Yeah. So right. So you're looking at this as the unit tangent bundle, and I'm just claiming that it has a natural action on the real line. Probably there is a direct connection. But all I can say is you can view this as a universal cover of PSL2R. And then it's a trivial lifting from the circle action to the real line action. So that's indirect connection. But probably I think it's interesting question to find the direct connection from that manifold, the tangent bundle to the real line homeomorphism group. So the Rain-Klebsin Navas prove in their ACTA paper, they prove two things. So first thing is if you have if you have a finitely generated group inside F1 plus S1, then either there's some invariant probability measure, mu, or there is some very special element such that it has only hyperbolic fixed points. So fixed G is finite, and G not prime Xi is never 1. So this is a deep theorem due to these three people. So any finite general group not preserving an invariant measure, then it must contain some element with hyperbolic fixed point. And the second part of the result is that every countable group inside homeomorphism group of one manifold. Yes.
So this map from SL2R to Omeo of S1.
Yeah.
Is it not just the action of SL2R? What map is it?
Oh, this is just embedding. This is analytic.
Right, so that
Yeah.
one is not the map into Diffeo.
All right, this is Diffeo. Diffeo is correct, right? And then this is, all right, so everything about compactness, very good point. So this is actually you embed into analytic of the real line. Omega means analytic. But the whole point is it's not smooth on the compact interval. Compact interval. So Thurston stability is about compactness. So, well, he even relaxed the condition that it is half open, but there must be some closed part. So right, actually that's a very good point too.
0, 1 closed.
Right, closed and open, right. 0 is fixed point, that's right, that's right. So in particular, compact interval is subgroup of this thing.
Here you see R as the open interval from 0 to 1.
That's right, this is same as the 0, 1 of diff.
This side is okay. Because the R is just like 0, 1
Yeah. Right. So actually, that's very good point. Very good point. Right. So everything is about compactness. So every countable group, there is some H homeomorphism of M1 such that it conjugate into Lipschitz homeomorphism group. So I'll just call it as Lipschitz. The collection of all the by Lipschitz homeomorphisms of M is written as diff of Lip. So this shows that if you already know that T is orderable, embeds into homeo of the real line, then critical regularity is 1 because you can achieve regularity of 0.9 or 0.99 or 0.999. That's what this Lipschitz continuity is better than any lower regularity like 0.9 or 0.99. Basically, Lipschitz regularity is the best possible regularity for a continuous map. So critical regularity, although 1 is not achievable, you can achieve 0.9 or 0.99. Therefore, we conclude the critical regularity is 1. So this is an example of certain real number is realized as critical regularity of some finitely generated group. So possibly first example. And then there are many other examples that I don't have time to cover, just a few things. Plenty Thurston theorem asserts that every nilpotent subgroup inside diff2 is abelian. So in particular, for example, a Heisenberg group is a 3x3 integral matrix with ones on the diagonal, upper triangular with ones on the diagonal. It can never be C2 smoothable. And then there is a result by Castro, Navas, Rivas, proving that this Heisenberg group is 111Z may be embedded, say, into diff 2 minus epsilon plus of I for all epsilon. But diff 2 is never possible by Plenty-Thurston theorem. Therefore, corollary is that this critical regularity of Heisenberg group is 2 with respect to the interval. So 2 is achieved. And also there is a result by Porquera, Navas, and Rivas proving that critical regularity of one more nilpotent degree, 1111 and Z on the above is 1.5. But they do not know whether 1.5 is realized. They prove that 1.499 is achievable, 1.5 plus epsilon is not achievable. So another thing is, I'll just omit some of the background, but regarding the mapping class group. So mapping class group of, say, S is defined as the homeomorphism group quotient by isotopy, or homeomorphism group isotopic to the identity. And so in the case of one punctured surface, genus G with one puncture, there is a natural Nielsen section into the circle homeomorphism group. But the construction is very intuitive. So you consider a surface. So comma 1 means one puncture, so just one mark point. So there's a mark point, say X naught. Consider the universal cover, and lift is fixed. Then whenever you have a homeomorphism, you consider lift on H2 and prove that this boundary action is well defined. It's well defined. Well defined means it respects group homomorphisms and also Unicopter homeomorphism, Unicopter topological conjugacy. And this is circle. So this is how you roughly construct mapping class group action, faithful mapping class group action on the circle. And the question is, how smooth can it be? And the whole group turned out to be not smoothable because there are too many toxic relations. So it's due to Farb and Frank's, written in 01, but published in 1920 in Thurston Memorial, that the mapping class group cannot embed into diff2 of S1. The mapping class, I just omitted the mapping class group, cannot embed into diff2 S1, and for genus at least 2, and Parwani in 07 proved that it can never embed into even diff1 using Thurston stability for genus large enough. But for the remaining time, I'd like to talk about virtual question regarding this direction. So, and this will be really the end of the history. And next time I'd like to talk a bit about the proof of the construction, critical regularity group. So the real question is, does there exist a finite index subgroup of any genus and any puncture such that H embeds into if one of S1? And let's call this as conjecture A. Conjecture is there does not exist finite index subgroup embedding into diff1 plus of S1. And this is actually a lot harder and still open compared to the previous result. And one of the motivation considering this conjecture is another conjecture saying that for all H finite index subgroup of mapping class group, in other words, like in the similar form, such that H surject onto Z. So this is called Ivanov conjecture, that there does not exist any finite index subgroup having non-trivial upper H1. And another conjecture, maybe I should call this as a question, but just to be uniform, is that mapping class group has property T. And these three conjectures are roughly related in the following. The first one is no finite index subgroup can embed into diff1 of circle.
Why is it much?
Right. So because roughly speaking, the whole group contains a lot of torsion, which is something that you can exploit, and also braiding relations. But if you go deep inside finite index subgroup, all the torsions disappear, and whatever relation you thought you have will disappear in this deep inside the finite index subgroup.
Today you have, I mean, mapping class group has these subgroups. So these embeds in the class subgroup.
But it's not finite index subgroup.
Finite.
FI, right. So actually, I prefer to use this shorthand notation. That means finite index subgroup. Yeah. Right, so let's see. First of all, conjecture C trivially implies conjecture B. Also, I didn't define what property T is, but because it has never been defined in this workshop, so I'll just briefly say that for countable group, property T can be defined as property of fixed point existence for Hilbert action. So whatever isometric action of gamma you have on a Hilbert space, it must fix a point. So, and why is this true? Because if it has property T, then property T descends to any finite subgroup, so H must have finite property T as well. But if H hypothetically is surject onto Z, then it is non-trivial fixed point reaction on Hilbert space. So if H surject onto Z, that index into isometric group of Hilbert space without fixed point free. So contradicting property T hypothesis. So C to B is just trivially true and easy to prove. The other directions are not complete implication, but roughly related. So, right, conjecture A to conjecture B is most relevant to this talk. That or actually, yeah, conjecture B is stronger. Conjecture B is stronger. So if there exists an embedding of H inside diff1 plus of S1 for some finite index of global mapping class group, and say assuming genus is large. So assuming genus is large. Okay. Then you can find two direct products coming from decomposition of the mapping class group into two parts. So consider the subgroup supporting on the left part, consider support on the right part only, and take a finite index subgroup. Then HIs are all finite index subgroups of some mapping class groups. HI is finite index subgroup of some mapping class group. So this is S1 and S2. Okay. Then it's easy consequence of de Roy-Clebson-Navas that H1 or H2 preserves a measure. Because everything is finitely generated, so you can apply their theorem. So either preserves a hyperbolic fixed point, but if H1 has some hyperbolic fixed point, H2 must preserve a measure, actually atomic measure. And in this case, you can show that, say H1, for instance, then the rotation number becomes a homomorphism because it preserves a measure. So rotation is just simply homomorphism. And then using this, you can show that some finite index over H1 must surject onto Z. Okay, because you already have homomorphism. Okay, so this contradicts. So this gives you that some fixed point, so H1 prime embeds into. So global fixed point. There is a global fixed point of some finite subgroup. And then this gives you a contradiction. Because then Thurston stability, H1 prime must surject onto Z, but Ivanov conjecture is asserting that it can never surject onto Z. So these are related, so therefore, we studied finite index subgroups of these things. So there are some known results. I'll just conclude my talk with these known results. So with Beck and myself and Kuberda, we proved that some finite index subgroup can be embedded into diff2 if and only if mapping class group is virtually free. In other words, 3G minus 3 plus P is at most 1. So other than trivial case, it can never embed into diff2, even if you're taking finite subgroup. And also we proved that we couldn't resolve genus 2 case, but if 3G minus 3 plus P is at least 3, I mean, not once punctured 5 once genus 1, 5 punctual torus, we do not know an answer, but it's genus 2 or higher, then no finite index subgroup of mapping class group embeds into if 1 plus epsilon of circle for all epsilon. So we proved the epsilon version of conjecture A, but we couldn't prove conjecture A as is. Yeah. So whatever epsilon, so you consider you can never embed it there. Yeah. And I'll just say one word for the proof. The proof uses right-angled darting group because right-angled darting group has this very easy but useful property regarding finite index subgroups. So if A gamma embeds into some mapping class group, any group even, and H is any finite index subgroup, then there exists another embedding A gamma into H by taking certain powers of the generators. As using this, we exploit the fact that mapping class groups have certain right-angled darting groups, and the right-angled darting groups will persist in every finite index subgroup, and prove that such a right-angled darting group cannot be smoothed, algebraically smoothed. Infinite subgroup, yeah, certainly, yeah. This is very concrete. If it is generated by VI, index is n factorial, right? Yeah, VI to n factorial, yeah. You consider VI to the n factorial, and still isomorphic, yeah. So these are some of the lines that people have been interested in regarding algebraic smoothability. And still, this critical regularity is extremely hard to compute. But there's another result that I didn't mention by Andre Navas, that every property T group can never embed into diff 1.5 of the circle. And this outstanding conjecture that it can not even embed into diff 1 of the circle. So that is also, yeah, I have no idea, yeah. But like, to be safe, the conjecture is like diff 1 is not even possible. So I'll stop here, thank you.
Thanks very much. Any more questions?
So I have no idea. If one can prove the last theorem for diff 1, that would be really big news. Yeah. Because it will, right. It doesn't imply Ivanov conjecture, but it gives a very strong evidence for Ivanov conjecture. Right. So this mapping class groups, for example, if you have a genus 2 surface, then it contains a right-angled darting group of, say, free group cross free group star Z. That is generated by this two dentists generate some high powers of dentists generating free group, and another high powers of dentists generating another copies of free group, and some random dentist intersecting all of them. So take any curve and apply pseudonorms many times, then it will intersect everything, so that you have a certain Z factor. So this is an example of right-angled darting group. And so what we prove is this, actually this very specific group, F2 cross F2 star Z, can never embed into diff 1 plus epsilon. And because every finite next subgroup of this mapping class group will contain a copy of this thing. So we prove that this can never embed into diff 1 plus epsilon of this compact one manifold. Why? Right. So we try hard and show that there must exist some element having disjoint support. So some element A and some element B acting on the interval, such as these supports are disjoint by this group structure, using this epsilon part, and you just use some distortion argument. So the goal is find some A and B in F2 cross F2 such that supports are disjoint. So here tilde means support, complement of the fixed point set.
Typically, A would be in F2, B will be in the other F.
No, not necessarily in this case. Yeah, not necessarily. Yeah. So once you achieve this goal, then you can apply so-called ABT lemma, which is for C1, that you have if A and B of T are diff 1 of compact one manifolds, and if A tilde and B tilde are disjoint, then the group generated by them can never be isomorphic to Z2 star Z. So this is the separate lemma that we use. So because A and B have disjoint supports, so they will generate Z2 or maybe Z or trivial group, depending on whether A and B are trivial or not. But whatever T you consider, assuming the action is C1, there will always be a hidden relation regarding ABT. So it can never be free product. So once you achieve this goal, you can never have embedding of star Z because something will have disjoint support. So not here, but here. So to achieve this goal, so epsilon, 1 plus epsilon is needed.
So this support is disjoint in that both A and B have like fixed point size.
That's right. Yeah. Of course, but like the supporting intervals can be countably many, like can accumulate, but still, yeah.
You can just get some generally you produce a much bigger.
Oh, so you're saying how? Yeah. Right. Fixed point sets are most definitely not most often not countable. Sure. Yeah.
But this is related to the structure of
Or so you mean how to achieve this goal? Yeah, how to achieve this goal? Right. Right. So it requires some classification of actions actually coming from this direct product structure. So not necessarily this thing, but let me give you another example just to illustrate how these things might happen. So another theorem or lemma is that if you have this is mentioned yesterday actually, this Baum's-Lux orbital group acts on if 1 plus of interval, and let's call this as C cross AE, where A inverse is E squared. Okay, this is hypothesis. Then C tilde and E tilde is disjoint. So this is one example of this kind of phenomenon, that group structure forces that certain supports are disjoint. And why is this happening? Well, assuming they intersect, then you can reduce the situation to such a thing that you have C acting on certain interval without fixed point. So like C is pushing everything to the right. And this is affine action. So something like affine-like action is infinitely repeating. So A and E acts like affine, A and E acts like affine. Like affine means A is like something like multiplication by 2, and E is like translation by 1. Something like this. So this thing infinitely repeats. But the problem is even this affine action, one can show that there exists some point such that A prime xi is 2. So something A prime is 2, some point A prime is 2, something A prime is 2, something A prime is 2. And this is absurd because A is fixed here, fixed here, fixed here, fixed here. Therefore, prime must be 1 here. So conclude that A is not C1 if this happens. So this is how you prove such a thing. So in this case, you prove that a certain point is not, cannot be, so some limit of the points have derivative strictly larger than 1. That is basically the only thing that you can use, you prove. So this epsilon Kölder continuity somehow assists us to make sure that certain derivative is stay away from 1 near the end point in this situation. Yeah. Yeah, so this is also kind of magical, right? So, well, so like, you know that action acting on A is acting on an interval without fixed point. Then it might not be conjugate to affine action, it might be just semi-conjugate to affine action, but still you can always find some point with derivative 2, remembering that A came from this multiplication by 2 action. So that requires also another page of explanation.
Any other questions or comments? Okay, so let's thank Sam again.
No, that's, yeah.